Inverse trigonometric functions, differentiation. Inverse trigonometric functions, differentiation. Now, you recall that we had introduced the inverse function for a particular function with the domain defined in such a way such that the function would be one-to-one. If a function is one-to-one, then its inverse exists. So here, the 6 trigonometric functions, their domains have been restricted in ranges such that to guarantee the one-to-one nature, thus guaranteeing the inverse function to exist. Here, the term arc sine or arc cosine, the arc just simply denotes inverse. So y is equal to the sine inverse of x if and only if you take the sine of both sides, you get sine y is equal to the sine of sine inverse of x. So the sine of sine inverse of x just gives you x. And that's the argument for the other 5 trigonometric functions as well. Here the properties is stating that fact. The derivatives, the last thing that we deal with in this section, somewhat difficult at first to grasp. You may want to commit these to memory, of which I do not recommend memorization, but in this regard, I will make an exception. So the derivative of the sine inverse of u is u prime divided by the square root of 1 minus u squared. Its counterparts, and all the counterparts, will be the same form, just negated. So the derivative of the cosine inverse is the negative of the derivative for the sine inverse. The derivative of tan inverse of u is u prime over 1 plus u squared. The derivative of cotangent inverse of u is negative u prime over 1 plus u squared. Then the derivative with respect to x of the secant inverse of u is u prime divided by the absolute value of u times the square root of u squared minus 1. There was an error here in the textbook, but the derivative of the cosecant inverse of u is negative u prime over the square root of u squared minus 1, then times the absolute value of u. I just want to make a statement here. If sine inverse of y is equal to x, then let's take the sine of both sides. Then sine of sine inverse of y is equal to sine x. Now sine of sine inverse of y is just y. So that is that y is equal to sine inverse of x. So we start with the first statement. That if we have this, then we're guaranteed to have this statement. That is the natural consequence. And they're both for direct implications one to the other and vice versa. Let's look at some problems and see if we can make some sense of that. Here you want to find these 6 trigonometric forms based on the right triangle, and that will be your argument for all of the algebraic problems that we're given in this section. We need to find this opposite side over here using the Pythagorean theorem. Say, for example, if this side here is equal to b, so what we have there is x squared plus b squared using Pythagoras is equal to 1 squared. So b squared is 1 minus x squared, and b comes out to be just 1 minus the square root of 1 minus x squared. So if that be the case, then the cosine of y is x divided by 1, or just x. Sine of y is the opposite over the hypotenuse. Well, the opposite is just the square root of 1 minus x squared. Tangent y is the opposite over the adjacent. So this is the square root of 1 minus x squared all over x. Cotangent is the reciprocal of the tangent, so that's just x divided by the square root of 1 minus x squared. Secant y is the reciprocal of the cosine y, so that's just 1 over x. And cosecant y is the reciprocal of the sine y, so this is just 1 over the square root of 1 minus x squared. And since I did most of that work up there, I'm going to pull this up so we take advantage of all of our space. Should be able to get all of that right there. Let's see if we can pull that up. Shouldn't need all that space, I don't think. Okay, good. I don't know how come I didn't do this earlier. Sorry. So evaluate without using a calculator. So if that be the case, then for part A, we look at that arctan of 3 over 4. I'm going to write this as tan inverse of 3 over 4. Let's say it's equal to some angle theta. Then what we have then is tan theta is equal to 3 over 4. So we're going to draw a right triangle. Here's the angle theta. And we label the tangent theta is the opposite over the adjacent. Using the Pythagoras theorem, we have the hypotenuse is the square root of 4 squared plus 3 squared. Well, so that gives us the square root of 25, or just 5. So if that be the case, then you're looking for the sine of theta. Well, sine of theta would be 3 over 5. This is the sine of tan inverse of 3 over 4. This is the sine of theta. And the sine of theta is 3 over 5. What about part B? So part B, we want to first find sine inverse of 4 over 5. Let's say this is equal to some angle theta. Then what that gives us then is sine theta is equal to 4 over 5. What we look at here, another right triangle with the angle theta. We label here sine theta is the opposite over the hypotenuse. Using Pythagoras theorem, we have here A is equal to the square root of 5 squared minus 4 squared Well, a comes out to equal to 3. So let's see what we have. We have the secant of sine inverse of 4 over 5. So this is the secant theta. Now secant is the reciprocal of cosine. Cosine of theta is 3 over 5, so the secant would have to be 5 over 3. Right? Cosine theta is 3 over 5. Let's move on to the next one. The next one, same argument, but what do you do with the negative sign? Well, we keep it consistent. So for part A, let's first look at sine inverse of negative 1 over 2. Let's say this is equal to theta. Then this implies that sine theta is equal to negative 1/2. Well, so here we have theta, and here it says sine theta, and so the opposite here would be negative 1, and then the hypotenuse is 2, and well, the hypotenuse is the resultant. Here we keep it positive, so it's either the x tender or the y tender is negative. Here it says sine, so sine runs with respect to the y tender. So we find this side, this would be the square root of 4 minus 1, or just the square root of 3. So now the cotangent of sine inverse of negative 1/2 is equal to the cotangent of theta. And remember that cotangent is the reciprocal of tangent. Tangent theta is this negative 1 over the square root of 3. So the cotangent would just be the negative square root of 3. What about part B? The cosecant of tan inverse of negative 5 over 12. So here we consider tan inverse of negative 5 over 12. Let's say this is equal to theta. This implies that tan theta is equal to negative 5 over 12. Again, we use our handy-dandy notebook right triangle, and we label. Here, the tangent theta is the opposite over the adjacent, and both of them can't be negative, because if both were negative, then the tangent would be positive. Here, typically, the tangent here being negative would simply mean that you're falling below the x-axis, and if that be the case, then it's the y tender is negative. So here, this is negative 5 over 12. This is the angle. Using the Pythagoras theorem, this side here, the hypotenuse, is the square root of 12 squared. Too much. It's negative 5 squared, but you square it's going to be positive, so it gives us 13. So here, the cosecant is the reciprocal of the sine. So sine theta is here the the negative was 12. I'm sorry, sine theta is negative 5 over 13. Thinking about cosine. And so then the tangent, well, the cosecant of that would be just the reciprocal of this. So the cosecant of tan inverse of negative 5 over 12 is cosecant theta. Cosecant theta is reciprocal of sine theta. So that gives us negative 13 over 5. We'll simplify here. Well, we look at the inside. So we look at secant inverse of x over 3 is equal to theta. And it's really, if and only if. I need to make that stronger. If and only if secant theta is equal to x over 3. That is, if we talk about secant, the reciprocal of that gives us cosine. So cosine theta gives us 3 over x. So it's the only problem that we have left. So I'll come down here and take the space. So cosine theta is the adjacent 3 over the hypotenuse x. So this leg here is the square root of x squared minus here 9. So now you want to find the tangent of this angle. So the tangent of secant inverse of x over 3, which is tangent theta, and the tan theta is the square root of x squared minus 9 all over 3. Now lastly, let's look at some derivatives. Here the derivative of f of t, f prime of t, according to how they define the derivative, this is going to be u prime, where u is equal to t squared. So u prime is 2t. This is all over here, the square root of 1 minus u squared, t to the 4th. Well, that's all there is. Then down here, you have that x squared times the tan inverse of 5x. We have to use the product rule with that x squared in terms of taking the derivative. So h prime, not h prime of t, but h prime of x is equal to the derivative of the first, which is 2x, times the second, tan inverse of 5x. Now then it's plus the first times the derivative of the second. Well, the derivative of the second is the derivative of 5x. Here u is 5x. So the derivative of this 5x is 5 all over here. The derivative for this tan x is defined as the derivative of u, or u prime, all over 1 plus u squared. So this is 1 plus 25x squared. So we can just clean that up and say that h prime of x is 2x tan inverse, or you can say arctan, plus 5x squared over 1 plus 25x squared. So just be careful with that, and I think all should work well. Thank you.